Okay, students, welcome back. In this video, we're going to start talking about isotopes of atoms, and we're going to be doing mass calculations based on atomic masses and so forth. I expect that this is mainly review for you, so hopefully you've seen this material before, and this will be just a refresher. So first of all, we come to our first statement here that atoms of the same element, let's assume that we're talking about carbon for a moment. Atoms of the same element carbon, let's say we've got two atoms of the carbon that have the same number of protons. Remember, the number of protons defines the element. So if you have 6 protons in the atom, we know that it is a carbon. So if you have more than one atom of the same element that have the same number of protons, but they differ only in the number of neutrons in the nucleus. So let's say you have 2 carbon atoms. That means they each have 6 protons in the nucleus, but they have a different number of neutrons in the nucleus. We call those atoms isotopes. Iso meaning same, topes meaning, well, it derives from shape, but isotope is the term we're going to use to differentiate them. So I could have 2 different isotopes of carbon. They would both be atoms with 6 protons, but they would have a different number of neutrons. When we add the number of protons plus neutrons in an isotope, that is its atomic mass number. Okay, atomic mass number. Atomic mass number. Now I'd like for you to take a look at the periodic table for a moment. Let's take a look at carbon. And notice this number here, the number 6, that tells us that's the atomic number, right? That tells us how many protons are in the nucleus. And that number is going to be true for all isotopes of carbon. Every atom of carbon has 6 protons in its nucleus. But what about this number that's below the symbol? Is that its atomic mass number? Well, remember that the atomic mass number is the number of protons plus the number of neutrons. But what's going on here? This is not a whole number. It's not just 12, it's 12.011. It's not possible to have a 0.011 proton or 0.011 neutron. Atomic mass numbers must be whole numbers because they are adding up the number of protons and neutrons. But very often we find numbers down here that are not whole numbers. That's because the number that is on the periodic table here, this 12.011, that is not an atomic mass number. Atomic mass numbers are always whole numbers. The numbers that are here, instead, are the average mass of an atom. So let's think about that for a moment. This carbon has many isotopes. Each isotope may have a different number of neutrons in it, right? So if you take the average mass of all the carbons, you're probably not going to get a perfect whole number because it's going to be an average mass. So that's what this says here. Notice that the atomic mass number does not appear on the periodic table. Instead, these numbers on the periodic table are the atomic number and the average mass. Okay? So let's take a quick look at isotope notation, how we represent the isotope symbolically. I'm going to use a large capital X to represent some theoretical chemical symbol. If it were a carbon, that would be a capital C, right? Then we're going to have numbers up in the upper left, down in the lower left, A to Z. You can think of this as alphabetically, A to Z. And then we can have a number up here that's a Q. Sometimes that's represented as a lowercase q, but I'll just represent it as a capital Q for now. So what do these represent? Well, obviously, the capital X is the chemical symbol. okay? This number Z is the atomic number. And what does the atomic number represent? It's the number of protons. And I'm going to abbreviate a proton as a lowercase p with a positive charge because we know that protons are positively charged. The number up here, this A value, is the atomic mass number. Now, to keep it from getting confused with atomic number, very often the word atomic is just left off and we call it the mass number. And what is the mass number? We know it is the number of protons plus the number of neutrons. And neutron, I'm going to give a 0 charge there because neutrons are neutral. Okay. Q over here. If this is a charged particle, an ion, then the Q is the charge. All right, like a plus or a 3 minus or a 2 plus or something like that. So that's an isotope notation. So let's take a look at an isotope notation of a carbon isotope. So we might have a carbon isotope. We know that its atomic number must be 6 because carbons always have 6 protons. Well, what about the mass number? Carbon has several isotopes, and 3 of them that are especially important to us. There's carbon 12, carbon 13, and carbon 14. So you might have heard of carbon 14 dating. Carbon 14 is a radioactive isotope that decays over time. So carbon 14 isotope, and that's what we're going to represent here. So we're going to give it the little 14 up there. So when you see carbon dash 14, that dash 14 is telling you that the mass number on this isotope is 14. I could have a carbon 12, which is what most carbon atoms are. That's the most stable form of carbon. I could have carbon 13, carbon 14, and so forth. So there is my mass number. There is my atomic number. If it is just a neutral atom, then what is the charge on a neutral atom? It's 0. It has no charge. So generally when something is not charged, we don't put a charge up there. Okay? Very often this number down here, the atomic number, is also left off because it's understood to be 6 if you have a carbon, right? So very often you will just see something like this, carbon 14. Or you might see carbon 14. Or you might have it written the way I've written it up there, carbon 14. All of those are ways to represent the carbon 14 isotope. So what does this mean? This 14. That means that it has 14 total number of protons plus neutrons. Well, how many neutrons are in the nucleus of this? If 14 is the number of protons plus neutrons, then you subtract the protons from it, subtract 6, and therefore it tells you that there must be 8 neutrons. So this carbon 14 isotope has 6 protons and 8 neutrons. Right? Okay. So that's how we write isotope notation and how we can interpret what it means. And here are some alternate ways of seeing the isotope notation mentioned. Okay. So now we have an exercise down here, and this exercise is a common exercise to get you to work with isotope notation so that you can calculate the various number of particles in a particular isotope's atom. So I'm going to do the first row across for you, walk you through it, and then I'll ask you to do the bottom row. So in the first row, we are given an isotope notation. We are given an ion, it's a 3+ ion, of scandium, and specifically the scandium 42 isotope. I'm not shown the atomic number here, but I know what it must be for scandium. Scandium's atomic number is 21. So I know that that must be a 21 down there, right? Okay, and I got that from my periodic table because that's the atomic number for scandium. So what are these numbers up here? Well, we know Z is the atomic number. Capital A is the mass number. This is the number of protons, the number of neutrons, the number of electrons, and the Q, the charge. So some of these things we already know. Z, the atomic number. That's the number of protons, right? And we got it right there, 21. Speaking of which, we can go ahead and plug that number in, right? Because that number is the atomic number Z, which is the number of protons, 21. Okay? What about the A number? That is the mass number, right? So the mass number is right there. It's 42. The number of neutrons. Well, if the mass number is 42, and the mass number is the number of protons plus neutrons, then the number of neutrons is the mass number minus the number of protons. So the number of neutrons equals the mass number A minus the atomic number, right? That's the number of protons and neutrons minus just the protons leaves you the neutrons. So we have A minus Z. Look at this, A to Z, right? You can think of it as A to Z. The number of neutrons is A to Z, A minus Z. So A is 42, Z is 21. 42 minus 21 gives us 21. It just so happens that in this particular isotope, we have the same number of neutrons and protons. That doesn't always happen. In fact, that often doesn't happen where they're the same numbers. But in this case, it happened to coincidentally be the case. All right, how many electrons? Well, we know that in a neutral atom of scandium, for it to be neutral, I must have the same number of protons as electrons, right? So if this were a neutral scandium, I would have had 21 electrons to be neutral to balance out my protons, right? But it is not neutral. It's a 3+ charge on there. So this is an ion. If electrons are negative, and I now have a 3 positive charge, does that mean I've gained electrons or lost electrons here? Well, if I had gained electrons, then this would become more negative, right? But it's become more positive, so that means I must have lost 3 electrons. So I have lost 3 electrons. So 21 minus 3 electrons to give me the positive 3 charge is 18 electrons. So there are only 18 electrons left there, which is why it's a +3 charge, 3+ charge. What is the charge on here? It's right there. It's the 3+. Okay, 3+ charge. So that's how we do this math. And the next 2 rows are going to be a little bit more challenging because I haven't given you the isotope notations. You're going to have to fill in the isotope notations based on the numbers that you're given here. If you've ever done a Sudoku problem, it's kind of like that, where you have to do some math here to figure out what the missing gaps are, and then write the completed isotope notation. So I'd like for you to do that. Please pause the video, and when you're done with both of those rows and completed the isotope notation for both, resume the video, and then I'll go over the answers with you. Okay, I'm assuming that you're coming back from doing this work, so let's take a look at what we have. For this second row, I have the Z. What is the Z? That's the atomic number, is 14. Well, if the atomic number is 14, where is that on my periodic table? It's right It's right here. Atomic number is 14. That must be a silicon, right? So we're going to write in Si for the element there. What is the A number? Well, the A number, remember, is the mass number. It's the number of protons plus neutrons. Well, I'm given protons and I'm given neutrons. So I add them together. 14 plus 7 equals, 14 plus 7 equals, and there we go. It happens to be 21. 21. By the way, I can go ahead and write in this number down here if I wanted to. It's not strictly required, because if I know it's a silicon, I also know this number has to be 14. But since I've got it, for completeness, I'll go ahead and put it in there. How many protons do I have? Well, it's the atomic number, right? It's 14. How many electrons do I have? Well, I would have started with 14 because I have to start with the same number of protons. But notice the charge is given. It's a 3 minus charge, which means I have gained 3 negative electrons, right? I've not lost them because this is negative. I've gained 3 negative electrons. So I'm gained 3. So the number of electrons is now 17. What is the charge up here? It's not 17, it's a 3 minus. And there we go, we finished the second row. Third row, all right. I don't know what this isotope notation is, but I'm told right here that I'm given a number of protons right there. It's 92 protons, which must also be the atomic number, right? That's the number of protons is the atomic number, Z. So 92 down here. What is the element with 92 protons in it? It's right there. It's uranium, right? So I now know the symbol for this, uranium. I'm given the mass number is 238. So it's the most common isotope of uranium, the 238 isotope, uranium-238. Number of neutrons, well, it's the A minus Z value, right? It's the mass number minus the atomic number. So 238 minus 92. And what do I get? I get 146. So there are 146 neutrons. Notice that the number of neutrons does not appear over here because it's included with the protons in that mass number. I'm told that I now have 88 electrons. So what must be the charge? Well, if I started with 92 and now I only have 88, it looks like I lost 4 electrons. If you lose 4 negative electrons, then you become more positive, don't you? So if I lose 4 negatives, I now must be 4 plus. And there's my ion charge. It's a 4 plus uranium-238 ion. And there we go.